In this scenario, the fixed point could really be used as a sort of pivot, so a connector between something more fundamental and physics below the Planck scale.
We often hear people talking about asymptotic safety, in particular in the context of quantum gravity. Before going there, can you please tell us what it means for a theory to be asymptotically safe?
Yes. So actually, the concept of asymptotic safety can be explained very well with an analogy. So imagine that you have a microscope and you zoom in into a system, a physical system. As you zoom in, you will see that fine details, physical details of what you see over your theory change as you zoom in, or if you want, since scales in the quantum mechanics are related, inversely related to energy, essentially it means as you go to higher energies, you will see your theories changing with the energy scale. In the context of the so-called quantum field theories, this means that the strength of the interactions have a dependence on the energy of the system. And as you zoom in, it can happen that the system reaches a regime where it doesn't change anymore. So as you zoom in or zoom out, everything looks the same. And you can think of this as zooming in into a Romanesco broccoli. As you zoom in, you will keep seeing always the same structures. This is what we mean essentially by scale invariance. And so as you change the scale, stuff does not change. And asymptotic safety is a particular realization of this scale invariance. So asymptotic really refers to limit of high energies or short distance. And then the safety, which also includes freedom as a particular case, and probably we'll come into that later, means that as you zoom in, your interaction couplings do not change anymore, so they will be constant. And this constant can be also zero in the case of asymptotic freedom. So as you reach a theory that is free from interaction couplings.
Okay, there's a lot to unpack here. So if I may stop you for a moment and see whether I'm following your reasoning. So you told us that quantum field theories, people here have heard a lot about quantum field theory, so we will not spend much time on that. We have quantum fields, they interact, they evolve in time, they are spread all over space. I mean, we know what we're talking about. Quantum field theories have some quantities, some objects kind of defining their properties, like coupling constants that tell you how the strength of an interaction, for instance, between two quantum fields and other kind of stuff. But let's take this example. What you told us is that as you move towards higher energies or shorter scales, these change, right? They change with the energy. Perhaps, you know, particles or fields, if you like, interact in a stronger or weaker or different way. But sometimes you hit a point after which they do not change anymore. They reach a fixed value. And if you keep zooming in, you keep seeing the same thing, like more or less, because you mentioned the cavolo romanesco, which is absolutely fine for us being Italians, but can use fractals as an example, like people might have fractals in mind. So is that the kind of idea you're referring to?
Well, whether asymptotic safety practically translates in a fractal structure of space-time actually is an open question. But at the level of the theory, reaching a regime where you have asymptotic safety or asymptotic freedom means that your dynamics is free from scales. So you do not have masses, if you want, in your theory. And there are, of course, examples of these theories. So, I mean, these type of regimes where you don't have scales are very important in many contexts. In condensed matter physics, for instance, scale invariance happen close to phase transitions. In the standard model of particle physics, we know in the theory of strong interactions, so interactions via the strong force between quarks and gluon, so in the framework of what is called quantum chromodynamics, the strong coupling varies with the energy scale, so we can measure that. And we see that as we zoom in, or as we increase the energy scale, this coupling gets smaller and smaller. So the interaction is weaker and weaker. And in the limit, as the energy goes to infinity, this coupling vanishes. It becomes zero. What does it mean that it becomes zero? It means that the theory has reached a regime where it is described by the free theory. So there are no interactions at all.
Which is much easier, right? Mathematically.
Which is much easier, exactly. And that's really the key point, because close to the free theory is close to what we call the perturbative regime. Why is it called perturbative regime? Because, well, as physicists, we always try to simplify models, simplify our systems such that we can move from stuff that we know. And the free theory is something that we can solve, we know how to solve. And then when interactions are small, so they are just a small perturbation on top of the free theory, we have everything under control. We know how the system behaves close to the free theory. And indeed, the free Lagrangian is free from scales. So it is one particular case of a fixed point. And then the concept of asymptotic safety is conceptually a small generalization of that. So one reaches a similar regime where your physics doesn't change anymore, but it does so with respect to an interacting theory. So not anymore the free dynamics, free from interactions, but with fixed values of the interaction couplings. And this is called asymptotic safety. So the couplings, if you want, or the theory is safe from divergences, because as you reach in the high energy limit a fixed point, should it be free or should it be safe, it means that your theory is well defined in the limit of infinite energy. And indeed, this is the starting. If you want, we can. I mean, I can just put the seed for our next conversation. That is asymptotic safety. Why does it have anything to do with gravity? Well, because defining the high energy limit of gravity with respect to the free theory doesn't work. So in technical terms, it means the theory is perturbatively non-renormalizable. Technical terms, but we can explain them later eventually. But it is possible, and this was Weinberg's proposal from 1976 that gravity can still be described within the framework of quantum field theory, which we know very well. We know it works for the other fundamental interactions, also for gravity, but if this can be defined at high energies with respect to such an interacting fixed point.
You made a couple of very important points here. Thank you for your answer. That I might try to summarize for our audience, because there's a lot of stuff we've discussed. So first of all, you mentioned an important fact, namely that asymptotic freedom and safety more generally do not only concern gravity, but any kind of theory, and they pop up in phase transitions and many other important phenomena. So we really are speaking about tools that physicists use in their everyday life, more or less whatever they do in theory when they use quantum field theory. And then you made here a distinction between asymptotic safety and freedom. So let me try to sum it up and tell me if you agree with my characterization.
Yes.
When these theories go towards the high energy regime, we call them asymptotically safe if they stop changing, right? If we have a specific interaction strength, for instance, particle A and particle B of two kinds interacting that way, and that's it, and this behavior does not change anymore, moving towards higher energies. Asymptotic freedom corresponds to the specific case in which that fixed behavior is interaction being exactly zero. Is this correct?
Exactly. Yes.
Perfect.
Precisely.
Perfect. Now, I might have a bit of a bias, but we are on the YouTube channel of the International Society for Quantum Gravity, so I would be happy to discuss phase transitions in metals and all that, but I'd try to focus our conversation a bit more on the problem of gravity. You gave me a nice hook there, mentioning perturbative non-renormalizability of general relativity, which is a classical, in the sense of non-quantum theory of gravity, the one we try to turn into quantum gravity with approaches such as asymptotic safety. Now, can you expand a bit on why it is so hard to turn general relativity into a quantum theory, and then we'll move towards asymptotic safety for quantum gravity?
Yeah, exactly. So that's a great question. So, you know, in the past century, we developed a lot of knowledge on how to deal with interactions with matter using the framework of quantum field theory. And that's extremely successful. So one could naively wonder, okay, why don't you just use the framework of quantum field theory and the tools that we know to quantize gravity? But the problem is that the straightforward or the application of standard quantum field theory techniques to gravity is complicated. It doesn't work right away, because it seems like if we try to quantize gravity in that way, we generate infinities. And this is something that in quantum field theory is known as non-renormalizable theories. So, and such type of theories are considered as effective. So theories that we can use up to some energy scale, but hit that energy scale, we need to replace that with something else. And a big question is being, well, how to modify gravity such that things can make sense. And it is really difficult, because one could think about, also based on the knowledge that we have with other fundamental interaction, one could think, okay, but how about modifying the dynamics of general relativity? So adding some terms maybe can make things better. We can remove the infinities. And it did this is a possible path. So one can add on top of the the general relativity dynamics, some additional terms. And they solve the problem of infinities, but they don't fix everything because one introduces new problems, and in particular a problem with unitarity. Unitarity is a key feature in quantum mechanics, quantum field theory. One can phrase it in different ways, and one way to say that is probabilities should make sense, so they should sum up to one at all times. And it turns out if one naively modifies general relativity, the dynamics of general relativity, one introduces problems with unitarity. So it seems like one has to decide between infinities and probabilities not making sense. And this incompatibility really led to a proliferation of approaches to quantum gravity. So each one modifying different aspects of quantum gravity, and it is really difficult to understand in which direction one should go. So for instance, relying on Hamiltonians rather than on Lagrangians, and then go in the direction of loop quantum gravity, or go in the direction of non-perturbativity, or modify the fundamental building blocks of nature. So for instance, going in the direction of string theory. So there are different possibilities, and it is not obvious. It is difficult to build something that is fully consistent. And the difference between gravity and the other fundamental interactions is that we don't have a guidance coming from data, because we think that quantum gravity lives at extremely short distance scales. So we can only rely essentially on internal consistency and perhaps observations, but only if there is some amplification effects that amplify the fine details of quantum gravity that live at extremely short distance scales. So we are talking about 10 to 19 GeV in terms of energy. And
Which is huge for people
which is
listening
huge.
and not be used
Yes.
to gig electron
Yes.
volts.
Essentially, it should be something like 20, in terms of scales, 20 order of magnitudes below the scale of atomic nuclei.
Yes, in length. Yes.
In length, yes. So now, the big question is how to build a theory of quantum gravity, and asymptotic safety is just one of the proposals, which whose idea, whose philosophy, because all of these approaches, if you want to need to take like one particular philosophy in how to address the problem. And the philosophy here is quantum field theory works so well for the other fundamental interactions. Perhaps we need just a minimal modification to make sense of gravity as a quantum field theory, and in asymptotic safety this bit would be non-perturbativity. So going from asymptotic freedom to asymptotic safety.
Before we get there, because that's the main, main part of our conversation, and thank you very much for the complete answer. Let me see whether I'm following. Gravity is complicated. I mean, the general theory of relativity is amazing. It's elegant. People love it. Everyone tries to, do a general relativity course in the masters. But when you try to turn it into a quantum theory, you told us that applying standard techniques doesn't really work. You get infinities.
Yeah.
And for people listening to us, when we say infinities, we really mean like the theory telling you that something you should be able to measure blows up to infinity, which doesn't make sense. Yeah. Right. For a variety of reasons, which I hope are clear, or we can discuss that further. Now, if we really want to tackle the problem of quantum gravity by, instead of, switching subject right? Because that's the only other option. Something needs to change. We need to tune or change a little bit of one of our techniques. Something needs to be different from what we did with electrodynamics. And in your case, in the case of asymptotic safety, which we'll discuss now, the main point is dropping the assumption of working in an asymptotically free context, namely a theory with no interaction with small perturbations, and moving to an asymptotically safe context, precisely as defined
Exactly.
before. Is that
Exactly.
correct? And if so, feel
Yes.
free to get into the, into the meat of asymptotic safety.
Yeah, I mean, precisely. So the idea is gravity may be defined more as a quantum field theory, but in the very high energy regimes, it doesn't flow, it doesn't reach the regime where it is weak. Rather, its interactions reach a fixed point where the interaction couplings are finite. And if this picture is correct, of course, I mean, one needs to verify whether this assumption, this conjecture is true. And, I mean, the conjecture, as I mentioned, came from a paper or two papers by Steven Weinberg proposed the idea. But then one cannot just assume that one has to test that. And the way that works is testing whether the dynamics and the renormalization group flow of the dynamics actually leads us at high energies towards this fixed point. And if this is the case, and this, based on the computations of the past 20 years, seems to be the case, then it is a promising idea. I mean, of course, there are several theories in the market, but what I like about asymptotic safety is that it is really the minimal modification that you can do, and if it works, you gain a lot because you are still in a framework that you control. You can connect with the physics that we know at low energies with really minimal effort. So at low energies, we know that we can parameterize the deviations from general relativity using the framework of effective field theory. So one just writes down higher order terms that correct the dynamics of general relativity. And at the end of the day, in a way or another, no matter how difficult your theory of quantum gravity is, the quantum correction that come from quantum gravity will be packed in these coefficients of the expansion that parameterize the deviations from general relativity. And in asymptotic safety, of course, there is quite some work that one has to do, but it is conceptually known how to derive these corrections. And one doesn't only derive the correction, one can do that also quantifying the predictivity of the theory. And this really boils down to how quantum field theories work, in particular those that whose high energy limit is defined by a fixed point. Because the properties of the fixed point already tell you the number of free parameters in your theory. And it looks like in asymptotic safety this should be free, at least if one considers the case of pure gravity, but also depending on the matter content that one adds to the theory, which is of course very important because gravity is not there on its own. There is a bunch of matter, there are other fundamental interactions, so it is really important to consider them together. And the whole theory will tell you exactly if there is a so-called ultraviolet completion in this sense, so this fixed point that happens at high energies, and how many experiments I have to perform at low energies to completely fix the theory.
Well, there's a lot here, so let me get into a few points you mentioned, because this is extremely interesting for me. I've worked on different things, and this really sounds like a minimal approach, and usually minimal approaches are to be cherished, and because
Yeah.
the fewer choices you make, the smaller the chance you're wrong. But despite the fact we are all wrong always and all that, we all, especially in quantum gravity. But when you say that in the last 20 years, let me go a bit back, 20, 30 years, there's been computations showing that there might actually be this kind of asymptotically safe fixed point for gravity. What do you mean exactly? What kind of computations do you have in mind? Can you tell us something more about that?
Yes. This reconnects with the way we started the conversation, so about what is asymptotic safety, and I started saying or trying to explain that physics, the dynamics of physical systems changes with the energy scale. This is just the concept. We know that at high energies it could go to couplings, interaction couplings could go to zero or could reach a constant value, or in non-renormalizable theories they might diverge. But now we have to get precise and try to understand exactly what is the variation of the theory with respect to the energy scale. And the way one does that is by using, by computing the so-called renormalization group flow. It is a flow, it is a change with respect to the energy, if you want, or the momentum scale. And renormalization group is, two interesting words that need some explanation. So imagine that we are looking at a system with some particles, charged particles, okay? And the normalization group, you can really see it as the mathematical version of a microscope. So as if you put in some if you can probe the energy scale or the length scale of a single electron, so you would be able to measure what is called its Bayer charge. So the charge that it has, if it would be there alone, not interacting with anything.
In its own
But
universe by itself,
yeah,
right? Everything.
lovely electron. But of course, as we probe physics, we can use probe certain energy or momentum scale. So perhaps we are not able to resolve that single charge, but we will see instead a cloud of other charged particles that surround the electron. And then what we measure is no longer the bare charge of the electron, but something effective, something that is the result of the interaction between the electron and whatever is surrounding it. And this is called dressed.
So,
Very
if
good.
I may jump in, and
Yes.
I apologize for that. What you mean is that if we examine an electron, but this applies to any kind of particle whatsoever or physical system, this is just a
Physical
simple
system
example.
in general, yes.
As we zoom out, when we actually measure some of its properties, we're measuring something which is influenced by a lot of physical processes we cannot see because we zoomed out. So we kind of average on them and get some result out of it, which is actually the product of a lot of stuff happening in electrons interacting with one another, other
Yes.
particles and all. Is it more or less the idea?
Yes, it is more or less the idea. And the power of the renormalization group is that it makes this idea much simpler. Because the idea of the normalization group is that as you zoom out from the scale that you want to probe, you can um, embed the effect of all the mess that is happening in changes in the interaction couplings. So you can describe literally the physics at different scales using the same objects, the same dynamics, but different values of the little parameters that appear in your theory. So you are rescaling, zooming out, rescale. And the normalization group tells you precisely, mathematically, how this goes as you zoom in, zoom out. And so this process, so this framework, the normalization group, then also allows you to understand how interaction couplings in quantum field theory change with the energy scale. So you can derive, for instance, the behavior of the strong coupling, so the interaction coupling that mediates the strong interaction as a function of the energy scale, and see that it goes to zero. And in the same way, we want to use this framework in the context of gravity to see what's happening with the interactions that govern gravity. It is just more complicated than usual because we need to use techniques that can detect or that can that are also valid when the theory is non-perturbative. So when your interaction couplings are not just small, so when you are not just around the little region close to the free theory, but you can have literally everything.
Yes, because as we said, within this context of asymptotic safety, once more, you allow your fixed point to be an interacting theory, not a free one, and so you can have
Yes.
two pictures around that. So the idea is more or less the following. You have a theory that works at a given energy. I have this machine, this tiny machine I call a renormalization group, or which sources
Exactly.
the flow, whatever that is. I want to know how my theory behaves at a different energy scale or length scale, whatever. I switch on this machine and it works and it tells me how my theory behaves at a different energy. So my question in that sense, before we go back to the main track of this course, I did not forget that, is why is this not straightforward? Because the explanation is quite clear. Why don't we just take gravity and check whether there's an asymptotic, safe fixed point? Is it that computations are much harder than it seems from our conversation?
Exactly. I mean, some minutes ago, you tried to summarize what I was saying, and you said, well, gravity is complicated. I think that this is like the best summary of the problem of quantum gravity. Everything is much more complicated than one could think, and as you try to circumvent a problem, you will get eventually another problem. So exactly, these computations are hard, but it's not only that they are hard. We have, this machinery, which is which practically is a differential equation. Okay, something more complicated than a differential equation, but just to give the idea. And the differential equation governing the normalization group is exact. So if you could solve that exactly, you could just get your answer, extract your predictions, everyone happy. But unfortunately, it cannot be solved exactly. If you want, you have to start with a little assumption on what your dynamics is, check the results, and then go one step further in complicating your life by adding extra terms and seeing whether by adding more and more terms your results are stable, so whether they converge. And indeed, there seems to be apparent convergence on the features of this fixed point, this interacting fixed point that governs gravity. And this seems to point to the fact that the theory is indeed asymptotically safe, so that this fixed point is there. But of course, this is not the end of the story. Otherwise, we would not be here with many people working on different approaches. So there are many open questions. So for instance, initially I mentioned another very important property in quantum gravity, as in any quantum theory, is unitarity. So the theory stated in one way or another, there are different equivalent mathematical formulations of unitarity, but in a few words, your theory must make sense. So your solutions should not explode, so you should not become very big, or probabilities should make sense, should
Yeah,
sum up to one, and all of this.
exactly. I would say I would stress that point if I may jump in, because
Mm.
sometimes people, when you say that, people respond, because this is, popularization, so we don't really get into the equation. So sometimes it seems like we just say we want the theory to be beautiful and that, but that's not the case. We're actually saying that just probabilities need to sum to one, because that's what probabilities are about. And if probabilities sum to -3 or plus 7.5, they just don't make sense. It's not something deep or mysterious,
Exactly.
right? So
Exactly. So
this
they should
is
sum up to one, and at all times. Because, of course, one could cheat and say, oh, at this time I can normalize my probability so that it is one. But then you can normalize once, only once, and then the sum has to be the same at all times. And this is the tricky bit in very
okay.
simple words. But, of course, it's more complicated than that.
So checking whether the this asymptotically safe fixed point, some evidence points towards, is gives you a unitary theory, is one of the big problems, right? But you were about, I had the feeling you were about to mention a couple of others. So can you expand a bit more on the open questions?
Yeah,
Still to.
yeah, of course. I mean, all theories have a bunch of open problems. I mean, in the context of asymptotic safety, I mean, especially in recent years, there has been some focus on the unitarity. I myself worked on that, and seems it's of course we still need to do a lot of work to test it, but at the moment it doesn't look like there are violations. So this property still needs to be investigated, but things don't look bad at the moment. But of course, one still needs to make precise predictions, and this is generally a problem in quantum gravity because things can be very complicated, and it is a little bit of an indetermination principle of quantum gravity. So if you want to be precise, you cannot say much, and then you cannot connect with the physics that we know. Make predictions that are actually relevant for observations. Perhaps you can make some precise placements for the high energy limit, but then if you really want to say something that has any relevance for astrophysicists or cosmologists, then one has to many times use models that are inspired by quantum gravity, but where the links are not fully understood. And then with these informed models that are quantum gravity inspired, so one can do some informed phenomenology, but of course from that to get precise answers on how quantum cosmology, or quantum black holes look like is really a big jump. And that's, of course, an open question. And another important point, and then we can zoom in one of these topics depending on what you like. There is also the question of connecting gravity with the standard model. So it is not sufficient that gravity works on its own. It also has to at least be compatible with the standard model. And ideally, also, depending on the theory that one looks at, reproduce the parameters that one sees in the standard model, or either reproducing or perhaps reducing the number of parameters in the standard model. And this is something that asymptotic safety seems promising at. So if you couple gravity with matter, so with the other interactions and matter degrees of freedom, you would already expect to get something out of it based on a completely classical argument. So in general relativity, space-time is influenced by matter and vice versa. So we have this very nice connection between masses curving the space-time. And essentially, this reflects in the quantum theory, in the fact that gravity and matter influence each other. So if I now want to compute the renormalization group flow of the standard model, there will be some effects of gravity on this renormalization group flow and vice versa.
It's what you mentioned before, right? Then as we
Yes,
zoom in or out, there's this mess, quantum mess involving all interactions, then
exactly. It's all
gets
coupled.
averaged, right? So if you work on the standard model, let me say electrons, electrons
Mhm.
nonetheless interact with gravity, right? Because they have an energy.
Yeah.
So when you have to average all this over all this mess, you need to take gravity into account. Is this more or less your argument?
Exactly. And of course, one could expect that, and I mean, this is generally the case, that quantum gravity effects are suppressed at low energy. But there can be still some non-trivial effect. So quantum gravity actually can, um, by the scrapping with matter, can allow to reduce the number of parameters in the standard model. So for instance, in asymptotic safety, we have a computation of the ratio of the top mass to X mass that seems to be very close to observations, also considering that we still use approximate computation, so I would say this is quite non-trivial. And also, speaking of trivial and triviality, we know that quantum electrodynamics, the quantum electrodynamics sector of the standard model has an issue. So an issue that doesn't really reflect, doesn't have consequences for the physics that we observe, because it is an issue that arrives at scales that are above the scale of quantum gravity, but still doesn't make quantum electrodynamics a theory that is complete, because it has the so-called Landau pole, so a divergence in the scale of the scaling of the coupling at a finite energy. And if you don't couple gravity, you can only remove that problem if you make the coupling zero everywhere. So the theory becomes so-called trivial. But what happens is that if gravity is there, it can enter the renormalization group flow of the fine structure constant in general of the couplings of the standard model. And it can actually create fixed points that were that cannot be there without gravity. And such fixed points could make the standard model, together with gravity, asymptotically safe and with a reduced number of parameters. And I found this very powerful. I mean, it is not only it is of course a bonus, because it is not written anywhere that the theory of quantum gravity must resolve these problems without ground unification, so without modifying matter. But I found that still find that impressive, and perhaps it's telling us something. So perhaps even if asymptotic safety turns out not to be realized at a fundamental level, perhaps we can still use it in the form of a so-called effective asymptotic safety. So it could be a low energy approximation of some more fundamental theory, I don't know, string theory, for instance, but could still be extremely useful in the bridging the low energy that we know with the fundamental theory that perhaps is works very well at high energies, but as that doesn't straightforwardly connect with the low energy world that we know.
So, in a sense, here, before I move to my next question, for which you gave me a very, an absolutely perfect conclusion of your previous question, because that's exactly where I wanted to go, so you can see my actions in advance. But let me sum this up, because this is an important point to highlight. Yes, it would be cool if gravity by itself were like asymptotically safe. But in our universe, we do not only have gravity, we also have matter, we have a lot of fields, at least those we describe with the standard model, perhaps others, we're not sure about that. And what we're actually interested is that gravity and the standard model kind of have a well-behaved asymptotic limit. This is my webcam sign. This is ridiculous. I was saying a well-behaved asymptotic limit together, right? Because they influence each other and they influence the way they go towards high energies. So that's what we're
Exactly.
interested in, right?
Exactly.
So this allows you to somehow derive, and this is my second check, the second thing I want to stress. Perhaps it allows you to derive some constraints on the way the standard model behaves, right? For
Yes.
this to work, when you include gravity within this asymptotic safety paradigm, you have some ratios, for instance. It only works if these two masses of these two particles are within this range of ratios, or if this interaction is weak or strong, or that. Is this more or less the idea?
Yes, it is the idea, and um, in just to connect the dots, you can understand that because the requirement of having a fixed point at high energies, so scale invariance, it means that you have a symmetry at the high energy. You are adding a little bit more to your theory. And I mean, anytime that you have symmetry, you have all additional constraints on your theory. So it is this scale invariance at the high energies that can allow to reduce, to add constraints, so reduce the number of free parameters in your complete theory. So for instance, standard model plus gravity.
That's amazing. So it's a whole package in a way.
Yes,
The whole package, and
exactly.
symmetries might involve both parts of the discussion. And here is where I want to go, because often quantum gravity proposals are portrayed as like rigid alternatives to one another, right? I think the universe is made of small cubes. I think it's made of small balls. So either I'm wrong, you're wrong,
Yeah,
or we are both wrong, right? But this is not actually the case. They try to address different questions. Some of them only tackle the problem of actually quantizing gravity. Some others involve matter fields and try to bring them to the same origin, or quantize everything altogether, change the degrees of freedom. I mean, things are a bit more complicated. And in this sense, I'd like to properly understand where asymptotic safety fits. You partially answered this, but I want to go a bit uh, deeper into this. Is asymptotic
exactly.
safety an alternative, for instance, to string theory? Something you mentioned, or they might be either string theory or other quantum gravity approaches in the end compatible with asymptotic safety, just for it just being a specific feature of quantum gravity.
This is a really good question. Of course, the answer is not clear, is complicated, but the possibility is there that different proposals for quantum gravity theories turn out to be physically equivalent. And just to give an example that maybe many could understand, in the context of quantum mechanics, initially the Schrödinger and the Heisenberg pictures were seen as two different theories of quantum mechanics. And only later it has been realized that they were two different mathematical equivalent mathematical descriptions of the same physics. And a question is whether this could happen to some of the proposals of quantum gravity that we know. So look quantum gravity, string theory, causal dynamical triangulation, asymptotic safety, Osava gravity. There are many. It could also be that different theories explore different regimes of this quantum gravity beast, or different aspects. So it is really, really important, first of all, at least in my opinion, to understand how the different frameworks work, and how to understand them in a similar language. Because, of course, this is in general a difficult question, because especially at high energies, if you look at the different theories, they really look different, especially because they speak different languages. And so, in order to translate one into another, we would really need a dictionary between the different features, the different aspects of the theory. There is one aspect where if all theories would be able to make a bridge, then it would be easier to compare their prediction. And this is something we already mentioned during our chat, and this is effective field theory. So we know at low energies we can parameterize the deviations from general relativity with some terms that correct the dynamics. And then the coefficients that stand in front of this correction pack both classical and quantum corrections to general relativity. So if every theory could come up with a prediction for these coefficients, then we could compare them and see if there is any overlap between them. And I think this is a very promising direction, though I understand that in some approaches to quantum gravity this may be easier than in others. So in asymptotic safety or other approaches that are based on quantum field theory, this is some work, but conceptually one knows how to do that.
And I would
In the
say that,
case,
if I may, extremely in line with the purpose of the International Society for Quantum Gravity, whose main
yes,
goal and drive is to make people belonging to different approaches of communities within the quantum gravity community speak to each other.
yes,
This kind of project is particularly useful even for putting people, in dialogue and make them interact and realize that perhaps they're saying
exactly,
the same
yeah.
thing with different words, right?
Exactly, exactly. And this is really um, a mission that I like. It is also part of my research, where I'm mostly focused on asymptotic safety, but I also have an eye on string theory, which I consider a really interesting framework, because um, it can it manages to be pretty consistent, like in terms of internal consistencies, but it is extremely complicated to connect it to observations, and really hit the standard model at low energies. But I still find it very interesting, and perhaps even if the approaches, say asymptotic safety, string theory, others are disconnected, so they are not equivalent. They it still makes a lot of sense to try to understand them together in a similar framework, or discuss what the most important questions are, because exchanging ideas and viewpoints allows to unlock questions or perhaps even techniques that we did not know before and that can help progress in individual approaches. So this can be useful in making progress in the individual approaches and maybe find intersections between them. Of course, this is not obvious. They could be just completely different, but it still helps a lot if we can exchange ideas and try to compare or understand individual approaches in the light or in the language of others. This is really, really important, I think. And if I can add one more thing, I think that asymptotic safety, aside from being interesting, at least in my opinion, because it is a minimal modification of a standard model and um, quantum field theory, and being able to predict what we some of the coefficients that we can see at the low, that we can parameterize at low energies. It is still, you know, it is written in the language of quantum field theory, and it may be valid at least up to the Planck scale, so it could literally act as a bridge between low energy and a more fundamental description. And this is called effective asymptotic safety. And even in this scenario, the fixed point could really be used as a sort of pivot, so a connector between something more fundamental and physics below the Planck scale. And this can be useful because one can still use the predictive power of the fixed point in order to extract parameters, and perhaps the more fundamental theory can also see this fixed point, if you want, from um, uh, a top-down in perspective, in a top-down manner.
So it would work as some sort of base camp into the wild, right? You don't
Yes.
really know what's next, but you construct this small house where you can always go back, where you know your stuff, and from there you keep exploring towards higher energies. Uh, and this is amazing, and I thank you for the clear explanations. I guess our audience by now will have understood why you decided to work on asymptotic safety. But if I may ask you a couple of more personal, not private questions, I would
Okay.
go slightly more general and ask you, because this might be super interesting for our young viewers, why you
Yeah.
decided to go into quantum gravity at all.
Um, okay. I I think this was in a sense the seeds of my interest for quantum gravity were already there, like when I was 10 years old or
Wow.
something like that. uh, because but of course, because I was somewhat advantaged because my brothers at that time were students at a university, so I could, and they were like one in physics, one in engineering. I could grab their books and have a look. And in particular, I mean, in that period, I also read. I mean, I was used already to work on logical problems and also some computer programming. I was already like with a mindset into math or related subjects. I remember I saw at that time a documentary on Enrico Fermi and the Vieni per guys, and Vieni per boys, I think it is in English. And for me, it was really interesting to see how theoretical physicists worked. And I like the idea of going deeper in understanding the mathematical structure of our universe, of the fundamental forces of nature. And at the same time, I read some books by, I mean, classical books by Stephen Hawking and Penrose, and that was already for me very extremely inspiring. And then jumping into when I was in university, after I studied general relativity, it was really um, um, love at first sight, if you feel like. I mean, I really, it was for me really fascinating how the properties of space-time and gravity could be explained in such an elegant manner via simple equations. And so after my master thesis, which actually was in a different direction, I thought, no, okay, I really want to do quantum gravity. And I mean, where in my university where I was, there was only one person working on that, and therefore I went into asymptotic safety. So this is like just in brief. But then I always had the idea that I wanted to explore or at least understand the different approaches, and in particular, I mean, string theory is one of those that interests me.
This is quite interesting because somehow, and researchers' lives often go this way, right? Even if people might not expect it at first, or we might not expect it as students when we go towards research.
Yeah,
Often research topics find you instead of the opposite, right? It really seems that asymptotic safety found you when you were looking for a quantum
exactly.
gravity project might fit your needs. In that sense, given the confusion that there might be around the life of researchers, my final question would be would concern whether you have any suggestion for students interested in pursuing a career in quantum gravity. What would you tell to that Alessia at the end of a master's degree deciding to do quantum gravity?
Um, so what I would say, I mean, it is of course a long path, like in understanding the details of quantum gravity, not only in one approach, but really understand what the deep problems are, and the caveats. And there is really a lot going on, and it is sometimes difficult to navigate the literature because many times papers are not self-consistent, and if you just ignored the literature and would not do stuff on your own, you would just go to a conference and hear 20 different opinions that perhaps are not compatible, um, are not self-consistent. So the thing that is really important in this field is to study critically the details of what you are doing, like in your approach, and try to understand and grab as much as possible of other viewpoints and research directions, because this is really important in understanding what's going on with quantum gravity, what the most important questions are, and this is a difficult field, so it is really important to develop your own ideas, also based, of course, on a thorough reading of the literature, but that must be really critical. So don't take things for granted. Try to reproduce calculations as much as you can.
I guess that with your call for critical thinking on the one hand and
Mhm.
open mindedness within the quantum gravity community on the other,
Yes.
this is a great point to thank you for your time collaboration and to wish you good luck with your future research projects. Alessia Platania, thank you very much for having spent some of your time discussing with me.
Thank you, Davide. This was very, very nice. I enjoyed our chat. And so thanks for inviting me as well. It was a pleasure for me.
Thank you very much. I enjoyed it as well, and I'm sure our audience did too. Thank you very much and see you soon.
Thank you, Davide.